this is one of the driest places on Earth. Sometimes it feels like being on the Moon or Mars.
During the day is a fantastic place, but during the night is absolutely astonishing.
So hi everybody, welcome to another CTAO event. Welcome on board of this journey through the extreme universe. I'm Alba Fernández-Barral. I'm actually going to be your mission commander in this journey through the universe, and I'm going to give you an introduction and I'm going to explain the roadmap that we are going to do in this webinar series. But before I forget, I would like to tell you that if you have any question, comment, you have a curiosity to share or your opinion, you can already do that in Facebook or in YouTube. We are seeing already some comments from people joining, telling us where they are from. I like that, thank you. So yes, if you want to share with us anything, do it all through the talk. At the end, if we have some questions, if we have time, we can get some questions and I will try to answer them. So now I'm going to show you the roadmap of this webinar series. Here we are. So as you can see, I'm going to take, the laser. As you can see, in this journey, it's going to last the entire 2021. So we initiate in April, but our latest webinar is going to happen on December. And this journey through the extreme universe is going to take us through the most extreme, exciting, exotic sources that our universe host. So we are going to talk about cosmic rays. We are going to see the different type of sources that we have in our own galaxy, in the Milky Way. We are going to see the spectacular sources we have in the extragalactic universe, in other galaxies. We're going to talk about the powerful transient events that just change the flags in seconds. And also, we are going to talk about the mysterious dark matter. We are going to understand how the CTA Observatory, CTAO, is going to be able to shed some light of these sources. Next month, on May, we are going to talk about the technology. We are going to delve into the telescope, their structure, the camera, how they catch gamma rays, what we see in the camera, the image that we see, how we store it, the data, and how we actually share it worldwide. As for today, let's say that we are still on Earth. We are not going to jump into the universe today. What I wanted to do is for us to learn some basic concepts that can be very useful, such as what is gamma ray astronomy, and actually what is a gamma ray. And also I would like to present the CTA Observatory, or CTAO. The CTA Observatory is the first ground-based gamma ray observatory in the world. It is under construction. We are going to have two telescope array, one in each hemisphere, so one in the northern hemisphere in the Canary Island of La Palma, and one in the southern hemisphere in the Atacama Desert in Chile. Before jumping into more details of the observatory, the telescopes, and so on, I would like to start with this basic concept I mentioned before. So let's start with the description, what we understand for high energy or very high energy gamma ray astronomy. So look, if you are watching this right now, you're probably an astronomer fan, or you're a very curious person about astronomy and science. So I'm pretty sure that if I could write also in the comments in Facebook and YouTube and ask you, what is astronomy, or what do an astronomer do? You would actually give me amazing answers. You can actually answer now if you want to. But a simple description would be that an astronomer observes the light that comes from some stars, galaxies, celestial objects, right? So high energy gamma ray astronomy is the same, but there is a specific characteristic in our field. We also study, observe, analyze the emissions of the light coming from specific cosmic sources, but this light, this emission, has an energy above mega electron volts. Don't get stressed about the electron volts word. It's just an energy unit we use in astronomy. The important is the mega electron volt, the mega part. Of course, if I say that, mega sounds really powerful itself, but doesn't really say us nothing. We need a comparison, right? So here you are. The visible light, the light we can see with our own eyes, the light that I have in this room, for example, has an energy of around 1 electron volt. So the sources that we observe in high energy gamma ray astronomy are sources with energies above 1 million electron volts. So now we start to understand this high energy part, right? Actually, this mega electron volts is the low edge of the gamma ray energy range. Gamma rays expand in a huge energy range. We actually doesn't know. We don't have well-defined upper limit for the energy range of the gamma rays, but we know that the lower limit is around the mega electron volts. In fact, the CTA Observatory is going to observe light that is around 1 billion and trillions times more energetic than the visible light. So really very high energy gamma ray astronomy. But one question could be why we want to observe this very high energy emission, right? Why don't we just keep with the visible light? Look at these beautiful images from Hubble. Look here, we have the Crab Nebula, a beautiful source, very important for our field, by the way. But why can't we just stay with visible light? Well, look, the visible light is just a very small fraction of the entire electromagnetic spectrum. So you probably know that the electromagnetic spectrum is a classification of the different types of light that there are in the universe according to their characteristics. So according to the wavelength, the frequency, the energy, which are actually correlated one to another. So the longer the wavelength, the lower the frequency, the lower the energy, and vice versa. So in this classification of light, in this electromagnetic spectrum, from the lowest energy up to the highest energy, we have radio waves, microwaves, infrared, then visible light, then ultraviolet, X-rays, and finally gamma rays. So now we know that gamma rays are the most powerful, the most energetic light possible. And as I said, the visible light is really a small fraction of this. You can see how many types of light we have, right? If we compare the visible light, its contribution with a piano, for example, it will correspond to an octave of a piano. But actually, not a piano like one that we can have in our home or that we can see in a concert. No. The universe, the cosmos, plays a 50 meters long piano. So you can really see how small this contribution is. If we would like to play a song and we would only could use an octave, it would not be complete, right? We really need to observe, we really need to hear the rest of the contributions. So this comparison was just to highlight the importance of observing different wavelengths, different energies with different instruments, of course, because each of them is going to provide different information, as you can see in this image of the galactic plane. It's not the same what we see in the optical, it's not the same from the near-infrared, X-rays, and gamma rays. By the way, in this journey through the extreme universe, we are going to have a very interesting talk, a very interesting webinar about the multi-wavelength and multi-messenger astronomy. That is when we observe one source with different instruments that observe different wavelengths or even different messengers such as gravitational waves or neutrinos. It's very interesting. I'm not getting into detail in this field because Sera Markov, she's actually going to shed some light in this field. Okay, so here we have an electromagnetic spectrum, a bit more technical, let's say. So here is the classification with the energy. On the left, we have the lowest energies. On the right, these are the highest energies. I'm not sure if you can actually read the text. I think it's very small, but I'm going to read it for you. So here we have again radio waves, microwaves, infrared. This part here is visible light, ultraviolet, X-rays, and gamma rays. So the first thing we realize when we have a look to this image is that the gamma rays have covers a huge energy range, right? And as I mentioned before, this part is not well defined, so there is not a well-defined upper limit. This would keep going here. But in any case, this already helped us to compare it with the visible light I mentioned before. It's around 1 electron volt, and actually it doesn't even arrive up to 10 electron volts. So in the gamma ray field, we have the mega electron volts again, so the lowest energy gamma rays. Mega electron volts was 1 million electron volt. Here we have giga electron volts, so 1 billion electron volt. Here we have tera electron volts, so 1 trillion electron volts, and here we have peta electron volts, and this is too much. We actually never detect peta electron volts so far. One thing that I would like to highlight here, which is very interesting, is the fact that the most energetic gamma rays, so the upper part of the electromagnetic spectrum, cannot be produced on Earth. There is nothing that is powerful enough to produce such energetic gamma rays. So in order to study these gamma rays, in order to study this part of the electromagnetic spectrum, we need to observe the universe. We need to perform gamma ray astronomy. So this is very important. Look, without gamma ray astronomy, a part of our knowledge, a part of the nature, a fraction of physics would not be reachable, would be missing, right? Here I'll also show you the energy range that we are going to observe with the CTA Observatory. As I write here, it is an unprecedented energy range. It goes from 20 GeVs up to 300 TeVs. This is the first time we are going to see such broad energy range, and especially with the performance we are going to see, so with the sensitivity, angular resolution, and so on. So look, this 300 TeV means that CTAO, the observatory, is going to observe gamma rays that are hundreds of trillions more energetic than the visible light we see with our eyes. So it's kind of spectacular. I mentioned before, we need to observe the universe to really understand, to really catch these gamma rays and be able to analyze them. But can we observe any part of the universe? So can we point our telescope to any star? Can we point it to our sun to, for example, observe the most energetic gamma rays? The answer is no. We need to observe the most extreme, powerful, violent sources in our universe. We need colliding winds, we need explosion that produce shock waves. We need this kind of structure that is called relativistic jet, and we need that because only in this extreme environment, charged particles like protons or electrons, what we know as cosmic rays, can get accelerated up to almost the speed of light, so to huge energies. And then these particles interact with each other, or with the environment, and give rise to gamma rays. So we observe these gamma rays in order to understand these cosmic sources, to understand the physics inside, for example, to understand the particle acceleration. What are the mechanisms that produce particles to move almost to the speed of light? So why don't we just observe cosmic rays for that? Why we have to observe gamma rays, which are a product of the cosmic rays, right? Because as I said, cosmic rays are charged particles, and our universe, the interstellar medium, the intergalactic medium, is full of magnetic fields. So cosmic rays are just like a magnet in all of that and get deviated. So, for example, we have here a cosmic source. So if a cosmic rays goes out of it, it could just go deviated and get lost here, for example, or it can go deviated in all the magnetic fields and get lost there, or it can actually follow this green curvy line you see here and reach our observatory. But if we try to track back its origin geometrically, it would say that it came from here, and we know that's not true. So that's why we use gamma rays, because after they get out of the cosmic source, they just move straight to the Earth. We catch them here in the observatory, and we can actually track back its origin and study the cosmic source, study all the mechanisms, the physical mechanisms that happen inside. And how can we detect those gamma rays? So here I show you another electromagnetic spectrum. Be aware, because this one has the energy backwards. So on the right we have now radio, the lowest energy electromagnetic radiation, and on the left we have gamma rays. This line here, this blue line that I'm showing you, that I'm marking, shows the altitude down which the radiation coming from the universe can actually penetrate. So we can see here in radio, the radio waves goes down all to the ground. But in the gamma rays, have a look here, our atmosphere actually prevents gamma rays to reach the ground. So actually our atmosphere is protecting us, right, from this super energetic light. So how can we detect them? Well, one option is to do it on the space and on satellites, but this has some limitation, especially at the highest energies. And another one is like the CTA Observatory is going to do by building Cherenkov telescopes on the ground. But how are we going to observe from the ground something that actually doesn't reach the ground? How we can observe gamma rays if they do not reach us? Because we observe them indirectly. So here I'm going to show you a fraction of the video CTA Science Emission to Discovery, which is available in our YouTube channel. I think it's a very nice video, because it actually explains all the process from the mission of a gamma ray in a source to the detection with our telescopes here on the Earth. So I really encourage you to watch it, not now, stay with me, but after the event, you can go to our YouTube channel and have a look to this very nice science animation. But here I'm going to show you a fraction of it to explain it myself. Here in this blue straight line represents a gamma ray, and the yellow orange lines, they represent the cosmic rays. So the gamma ray left the source and comes straight to us. You can see that the cosmic rays got deviated, but the gamma ray reached the atmosphere. There, it interacts with it and produces a pair of particles, one electron and one positron. These particles in turn produce light that produce more particles, more light, and so on, giving rise to what we call a particle cascade. These particles are extremely, extremely energetic. They actually move faster than the light in the air of the atmosphere. Attention, Nothing can move faster than the light in a vacuum. But in a medium, like the air or water, the light gets slower, and so particles with such energy can move faster than light. When they do that, it is produced a very fast bluish light called the Cherenkov light. So now we start understanding why we are called the Cherenkov telescope array observatory, right? So this light, the Cherenkov light, as I said, is extremely fast. It lasts barely 3 nanoseconds. That's 3 millionths of a second. So we can not really see it with our eyes, but our cameras can actually capture that light. So the Cherenkov light goes down to the ground, gets reflected in the mirrors of our telescope onto the camera. The camera of our telescope are extremely pixelized. They have a lot of detectors, and the footprint that the Cherenkov light leaves in our cameras has this kind of shape, this elliptical shape. By parameterizing this shape, we can get information from the primary gamma rays, such as the energy or the direction in the sky. I don't want you to get stressed from all this information. There is a lot, and it's actually a very innovative technique. In next month, in May, in the webinar about technology, Roberta Zanin is going to delve all into this. We are going to talk about this in much detail. The only thing that I want you today to understand is that the CTA Observatory, the Cherenkov telescopes in general, do not detect gamma rays directly, but we do it indirectly through the Cherenkov light produced after the interaction of a gamma ray with the atmosphere in these particle cascades. And in order to observe the Cherenkov light coming from gamma rays with such broad energy, so from 20 GeV up to 300 TeV that I mentioned before, CTA CTA needs 3 types of telescope, not only one. So here you have the small size telescope, the medium-sized telescope, and finally the large-sized telescope. You're probably wonder why they are called like that, right? I think we are very honest with the names of the telescope, but the small-sized telescope, the SST, has a diameter of 4 meters, the diameter of this mirror dish. The MST, the medium-sized telescope, the mirror dish has a diameter of 12 meters, and the LST have a 23 meters diameter. Again, I'm not going to get into a lot of detail in the technology. We are going to learn about it in next webinar on May, but I just want you to explain or going to mention briefly why we need 3 types of telescope. And it's because each of them are optimized for an energy range. So actually the small size telescope, they are going to be in charge of observing the highest, the most energetic gamma rays. This sounds kind of strange, right? Like the small telescope observe the highest part, the upper part of our energy range, but it actually what happens. The MSTs are going to observe the medium energies, and the LSTs, the large size telescope, they are in charge of the lowest energies, gamma rays, in the CTA energy range. And where are we going to have these telescopes? Well, I mentioned it before. We're going to be in 2 sites. We're going to be in both hemispheres. In the northern hemisphere, we're going to have a telescope array that we call CTA North. It is placed on the existing side of the Instituto de Astrofísica de Canarias, El Roque Los Muchachos Observatory on the Canary island of La Palma in Spain. CTA North is actually going to host only LSTs and MSTs. So it's going to be focused on the low, mid energy range of CTA. It's going to be built in phases. So the first phase is going to host 4 LSTs and 5 MSTs. We already have one telescope there, the prototype of the LST, what we call the LST-1. It was inaugurated in October 2018, and since then it was on the commissioning. Of course, it was a bit delayed because of the pandemic situation. So here you have a beautiful photo taken by Auger. It's a really amazing and beautiful telescope. I'm not biased, I promise you. It's really, really beautiful. And if you go now to La Palma, if you can visit the observatory, it's actually the first telescope you're going to see there. Okay, then the other side is in the southern hemisphere, and it's what we call the CTA South. It's located less than 10 kilometers southeast from ISO's Paranal Observatory in the Atacama Desert in Chile. And this one is going to actually host all 3 types of telescopes, so LSTs, MSTs, and SSTs too. So it's going to cover the full energy range. Again, it's going to be built in phases. The first one, we expect to have around 55 telescopes. But the CTA Observatory, CTAO, doesn't have only facilities in La Palma and in Chile, where we have the telescopes array and, of course, more infrastructure around. We have facilities also in Germany and in Italy. In Heidelberg, Germany, we have offices also in Bologna, in Italy. These are actually going to be the headquarters of the observatory. And in Zeuthen, near Berlin, in Germany, we have the Science Data Management Center. So where all the data from the sites is going to end up, all the software, the analysis tools that we make, that we will make available for the users in the future. And CTAO works with the CTA Consortium that is composed of more than 1,500 members from 31 countries. So we are a very international collaboration, very diverse, and we are actually very proud of this diversity. We actually are going to meet some of the CTA Consortium members along this journey through the extreme universe. They are going to explain us some of the science cases of the CTA Observatory. And just to finish, I would like to put CTAO in context with the ground-based gamma-ray astronomy history. So look, this field is extremely, extremely young. So the first Cherenkov telescope we had was Whipple in US, and the first source we ever detected at TeV energies was actually the Crab Nebula in 1989. So that was barely 32 years ago. That's nothing compared to optical astronomy that we've been using instruments for centuries already. The second generation was IGRA. It was the first stereoscopic system. It was located in La Palma. And then we had a third generation where we had HES in the southern hemisphere with 5 telescopes, MAGIC, the collaboration of MAGIC with 2 telescopes in the northern hemisphere. They're actually our neighbors in La Palma. And Veritas, which is a collaboration with 4 telescopes in US. So all these generations actually prove that the potential of the technique. We've been able to detect around 200 sources in gamma rays thanks to them. But as I said, this field is extremely, extremely young, and there is a lot of scientific and technological potential ahead of us. And that's why we are building right now the CTA Observatory. So just to summarize why the CTA Observatory is the future of gamma-ray astronomy, let me leave you with 5 characteristics. First of all, it's going to be the first ground-based gamma ray observatory in the world, and it's actually going to be the largest and most sensitive gamma ray instrument that we have in our planet. It is also going to observe as an unprecedented energy range, as I mentioned before. So from 20 GeV, we're going to be able to observe sources that are very far away, up to 300 TeV, so the most extreme accelerators. This actually, we're going to open a window here that we did not observe with the performance that CTAO is going to do. Also, we are going to be able to observe, we're going to have access to the full sky because we are going to have two sites. So far, all the Cherenkov telescopes, all the collaboration were located only in one of the hemispheres. So this allows us to observe the northern hemisphere sky and also the southern hemisphere sky. And with the better performance that we are going to have with the observatory, with CTAO, with a sensitivity better between 5 and 10 times better than any instrument right now, not only telescopes, Cherenkov telescope, but also satellites, we're going to be able to detect up to 1,000 new objects. So this is going to change our game. We're going to understand deeper the sources we already know. We are going to be able to detect new sources of different types. We're going to actually discover new types of sources. And of course, the unpredictable. I mean, if we are opening a new window of the electromagnetic spectrum with such a performance, of course, we are going to end up with something that we cannot predict right now, right? And finally, it's going to be the first ground-based observatory that is going to be open to worldwide scientific communities. So our data is going to be private for 1 year, and then it's going to be public, so anybody can actually analyze it. Also, the software, the analysis tools, they are going to be open, so any researcher, student in the world will be able to detect it. So that's it. Oops, that's it. That's what I wanted to talk about in this introduction. I hope you got excited in this journey through the extreme universe. I hope you are right now excited to learn more about these sources and this step ahead of us in the journey. I'm going to finish here. I think there are some questions. So I would like actually to invite my colleague, Megan. She's behind the scenes. So, hi.
So we do have, we have quite a few questions, but we have a lot of colleagues who've joined us from the CTAO who have been answering the questions for you correctly, I hope. There is one I haven't seen answered yet, and it is from Rupert. He is wondering about the PeV energies and why we have not detected them.
Okay, so actually, when we go to the highest energies, the flux of the gamma rays really decrease. So the amount of gamma rays that we have, because it's more difficult to produce them, right? So in order to actually detect gamma rays at PeV electron volts, we would need to have a huge collection area. So we would need to really have telescope around a very, very huge area. So that's why we did not detect them yet. Actually, CTA, as mentioned, is the first gamma ray observatory. Is going to be in the CTA South, where we have the SSTs too. It's going to cover a huge area in the desert, but we still can get to the electron volts. So maybe in the future, if we build new telescopes or techniques, we are able, but that's the constraint, the flux of the gamma rays.
Thank you for that. And actually, I think you did such a good job, and our colleagues that are following the event have done such a good job of answering questions. And I think that's it, unless I see anything come in the next few seconds. I think we're good.
I
on
like that. That team working.
Exactly.
Okay, so if there are not more questions, I would like just to thank you all for joining us. Again, I hope you get excited to initiate this journey through the extreme universe. Don't forget to subscribe to our YouTube channel and follow us on our social media so you can stay tuned for the next webinars. That's it. Thanks a lot to all of you. Thanks, Megan, and see you
Thanks,
in the next
everyone.
event.
See you next time.
Ciao, ciao.